Hi everyone, and welcome to this Nordic Tech webinar titled Adding Device Firmware Update, DFU or FOTA support in nRF Connect SDK. So I'll be your host today, and my name is Ali Aljani. I'm a developer marketing manager here at Nordic Semiconductor. And I'll now hand it to Sigurd Helsvik. He will be the speaker of this webinar.
Thanks, Ali. Yeah, my name is Sigurd, and I work at Nordic DevZone, where I answer your questions and help people as best I can. My specialties there are security and bootloaders, but we tend to take cases a bit all over the place, whatever fits and whatever we want. So I'm here to talk to you about bootloaders, and we'll start from scratch about to explain what a bootloader is. And then we'll move on to device firmware updates. And for both the bootloader and device firmware updates, I will say why you would want to have those. And onwards, I'll talk a bit about the key concepts for bootloaders and DFU. And then some libraries, mainly multi-image builds and Partition Manager, which you need to know about to configure these things. And after that, I'll do a hands-on demo. And I'll say it now, and I'll say it a couple of other times, that there will be a Dev Academy course, which I based this webinar on. And I wrote the Dev Academy course as well, with good help from Ali and others. And if you want more in-depth things, because this webinar will only be a part of the webinar, but the webinar will be more in-depth, and so you can see that if you want more. And I'll continue to remark on that. You should check out the Dev Academy. They are really good guides, and kudos to Ali and his team for making these. I think it's so good for you guys to have something to get started with our products for, in addition to our documentation. I think they're doing a great job. Okay, anyhow, when we want to know about bootloaders, let's start at the very beginning, because I'm assuming that I'm doing this assuming that you don't necessarily know what the bootloader is, just so that everyone is following. Um, Microcontrollers have memory. And you have two types of memory. You have volatile and non-volatile. The volatile memory, which is reset on every reboot, is often called RAM. And the non-volatile is called different things, but on the 52 and 53 series and 91, it's called flash, so I'm used to calling it flash. I should say that on the 54 series, it'll have a new name, but I can't remember it from the top of my head, but yeah, so we generally say non-volatile memory to have a catch-all term. Sometimes also refer to a persistent memory because it's persistent. And the key thing with this is that when you reset the chip, it's still there. So we use it for multiple things, but the main things we always use it for is to store our application. So when you see at the left side of the screen here, you see that the memory is ordered in addresses. So at the bottom of the memory, you have address 0. And since the nRFs are 32-bit memory, every one of these have 32 bits in them. And then it goes upwards with addresses and just moves up 0, 1, 2, 3, 4, etc. And it's like this dot 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 is quite large. I think, and these are hexadecimal numbers because we work with hex. And I think it goes to the 52 has 1, 2, and then 4 zeros. Yeah, it's a large address space. Anyhow, you don't need to know exactly how large it is, and our compilers and build systems will tell you how large they are. But important thing is that we store our application in this memory, and it'll look something like this. And I'll use similar illustrations later in this webinar as well. But they start with 0 at the bottom, and the app goes upwards. When you run the app, when you start a microcontroller, after it's done with like the basic setup of its peripherals, the CPU will run. And the CPU will start from 0 here, and then on whatever on that address. And then it'll follow the instructions there and go on from there. It is, of course, a bit more complicated on how it works underneath it all, but in general, we can simplify it to it starts at 0 and it goes from there. Now, a bootloader is something that boots the application. It runs before the application. It's in the name, bootloader. It boots and it loads the application. And it has, so as you can see from the previous one, similar to the previous image I have, the bootloader now is at 0, and whenever the bootloader is done, it'll jump to the application. So it'll point to the start address of the application from the bootloader. And the bootloader is some code. It is like an application. In many ways, it's often smaller, more compact, because you want it to be as small as possible to allow for the least amount of things to go wrong, but you also want it to do enough things so that it does what it needs. It has two main purposes, the bootloader. It will boot the application, as I just talked about, and it will verify the application. This verification I'll talk about in next slide, I think. And the booting I've already mentioned. And I promised you to say a bit about why you would want a bootloader. And the booting the application is it's nice to not go directly into the application and have something that runs before it, so that you can update the application. Now, when we have this bootloader at the start, which cannot be changed, and I'll talk about why it cannot be changed later, but we assume that it can't be changed for now. We can update the application, which is one of the large reasons to why you want a bootloader, to enable for DFU. But we'll get to DFU later. And DFU stands for Device Firmware Update, by the way, if that wasn't clear, if you haven't heard that before. Now, the second reason is for security. The updating to allow for DFU is a security mechanism, because if there's a vulnerability in your application, you can update it. In addition to this, the bootloader can check that how the application looks through verification. And as I said, I'll explain how that works briefly. But we are getting requirements, both expectations from customers, and also there are coming more and more regulations that require security. So because of this, you want to have a bootloader because it's mandated by regulation often. So remember to check that before you launch your products. If a regulation do mandate security, and if they mandate that you have a bootloader, chances are they will. Oh yeah, I should mention that when you are developing, you use a programmer, but this programmer is extra parts and it'll be expensive, so you can't just go around in the field on your products in the field to program it, and that's why you want DFU, because it allows you for the device, the nRF microcontroller, to be connected to and do like updated as it is without any extra parts to it, making you save a lot of resources for the programming. And often with the wireless things, you can also update them via DFU wirelessly. For example, for the 9160, you can send updates to the device from the cloud, which is very powerful. Okay, I promised to talk about verification, and here we are. There's a lot going on in this slide. I like the pictures take up so much space that I didn't have place for any text, but and I'll do that a couple of times, but I'll explain it. And if you want more text, there's always the Dev Academy course that you can check. And the Dev Academy course will also look into this a bit more in detail. However, The bootloader verification is a general concept, which is why this isn't explained in our documentation exactly how it's signed and so on. So I'll go over it here. And you can also find generic document, like if you search how does a bootloader work in bootloader security on the internet, you'll find a lot of guides on how this works in general, and it works the same way for us. So what we want to do, our end goal with verification is that the bootloader will be able to verify the application. It should be able to look at whatever application is running, and it should see is that whatever the person owning this chip has. So it can only boot my code and nobody else's. Now, we do this. And this process, to be able to do this, we start on the developer system, like your system, my system. And there we generate a private key that only I have and that I will keep safe. And the private key does not go on either the app or in the bootloader. It is on my system and I'll keep it behind lock and key in a secure place. With this private key, I can generate a public key. This public key is not secret in any way. It'll be used to, anyone can know this. And this public key is put inside the bootloader, just inside the code, not secret, just lives inside the bootloader, compiled as part of the bootloader. And then I take the private key and I sign the application image. The signature will be, it's cryptographic, but and I'll not explain exactly how it works, but part of it, which is important to know, is that it will calculate a hash of the application and then sign that. That means from this hash, I can later calculate the hash of the application and get the same hash from the application every time so that and only that application can generate that hash. Meaning, okay, so let's remember that the hash, it'll calculate the hash of the application and use that to sign. Okay. Now I have a signed application and I have a public key in the bootloader. And then we go to the side here in the middle. And we have two scenarios. We have one where it doesn't, where the verification is successful, and one where it isn't. So first, the bootloader. So for the verification, the bootloader with the public key will have a look at the signature here. And via the magic of cryptography, I won't explain how. Just if you want to know how, you can look it up on the internet or look at the Dev Academy guide. We can use a public key to look at the signature. With the public key and the signature, the public key can be used to verify that the signature is from the private key. And with that, no one else can generate that signature. We know with the public key that the signature is only by the person who owns the private key. So because the public key is in the bootloader can know that the signature was only generated by me. It's only by, so you know it's your own firmware. However, you also, so that no one just gets your signature from a random place and puts it on their app, we also need this. That's where the hash part is important. The signature also has a hash so that you know the signature is from me and you can look at the signature and use that to verify that the application matches the hash in the signature. And that way we know both that the app was not changed and the app was from me. And then when we have verified this, we do the normal booting thing and we run the application. However, if the signature is missing or wrong, or the application doesn't match the hash, we try to verify and it fails. And as you see, there's no running. So the bootloader will just say, give an error message like the app is not recognized. Sorry, we couldn't run this. So that was a brief overview over verification. It's a bit complicated, but it's a generic process with public-private key pairs, cryptography, and there's a lot of resources on this. So look at the Dev Academy, look online if you want to know more about this. But I hope this made some sense. Now, I was saying that you want DFU, so you can update your bootloader without a debugger, or update your application without a debugger. And that's where we are now. I'm going to tell you how device firmware updates work. The point here is, as said, to transfer a new firmware to your device. And this is done in 2 steps usually. You need to transfer the firmware image from another device to your device, and then you need to write the firmware into where it will live, usually into the application slot. Because the bootloader points to some addresses where it should start running from, so your new firmware should usually be put into start at the same addresses. Okay, I want to mention that I'm going to say DFU and FOTA. DFU is for device firmware updates, and FOTA is for firmware over the air. And FOTA is just DFU to update the device, but it is over the air, meaning over a wireless protocol. So it's typically used alongside Bluetooth or LTE or other wireless protocols. But they're essentially the same. You can just say DFU over Bluetooth and it will mean the same as FOTA over Bluetooth. And then we have 2 ways to do DFU on, especially in MCUboot has these 2 names for it. First one is serial recovery and the other one is dual slot. Dual slot I will get to in next slide, but serial recovery is a bit more straightforward in some ways, so I'll start with that. Serial recovery is as in the image here, that you have the bootloader and you have another device on the left side with the new app, and you have your app running here, a bootloader and a new app. Now, here the thing that receives the app, let's go from the start on the video. The receiver of the new application is in the bootloader. There will be some serial code, by default UART for MCUboot, to receive the updated, the new image, and then the bootloader will overwrite the application with this. So you will see this new app here being transmitted through the bootloader and written to this, and that'll look something like this. Yep. This all the images in this presentation is from the Dev Academy course. So if you want to play GIFs multiple times to see what they do again, you can go to Dev Academy. Okay. The reason why this is named serial recovery, and the main reason to use this, is that it runs all of the updating code is run in the bootloader, meaning that if your application crashes, then you can just go into bootloader mode again and upload new code, because it will be able to overwrite the application no matter what state the application is in, which is recovery. The reason why it's called serial is that it uses the UART protocol to receive images. And the reason for this is that any large code, a large protocol such as Bluetooth or other wireless protocols, will not fit inside the bootloader quite nicely. Those are typically large, and therefore you don't want to put them multiple times into your memory, the Bluetooth stack, and other such stacks. So therefore we would like to run those in the app if we want to do DFU over any wireless protocol. And that brings us to next slide. To do wireless DFU or FOTA, we need 2 slots. But why do we need 2 slots? Well, previously Yeah, as I said, the wireless protocol needs to be inside the application image. However, if the image here receives the new file, then it cannot overwrite itself. Because if you try to write to some part of Flash from the parts of Flash that you're running code from, bad things will happen. Therefore, we need to write to some other part of Flash to save the image that we received. That will be the new image that we run in another place of Flash. For this, MCUboot splits Flash in two. Well, three. There's a small partition for MCUboot, which is this figure is not to scale, which will be a lot smaller than the application. Then the rest of the memory is parted into two equal parts, like this, where the one the application runs from is called MCUboot primary, and the other one is named MCUboot secondary. I just mentioned these names so you've heard them before, because when you develop, you might run into them. If you want some other storage on your device, you could of course add that as another application, and another partition in Flash, and then yeah, the rest of it would be parted into MCUboot primary and secondary. Now, the way this works is that you have a device to send to your application. Your application will, let's say for an example, run Bluetooth, and then your device, the uploader, will be a mobile phone. Then that will transmit over Bluetooth to the application, and the application will write to Flash to the secondary slot. And here the bootloader has just booted the application as normal, and I've done nothing before this, so the application, you don't need to restart the application to start receiving the image here. You just use Bluetooth as normal. So then we will see how that looks on the video, or the GIF that we made into a video. Yeah, as you see here, it was transmitted into the secondary slot. And then the next step will be to reset the device. This is, or well, the next step is not to reset the device. The next step, like conceptually, will be to move this new app and overwrite the old app. But as we said, the application cannot overwrite itself. So we need some other running code to overwrite it. That's where we got the bootloader. The bootloader can then move, swap these two images. Well, we'll see how that looks on the GIF. First we reset it, we turn it off, and then the bootloader runs. And now that we are running the bootloader, it can overwrite the new image, the old image with the new. As we see here, it was moved down. Now, often we will, instead of just overwriting here, so we lose the old app, we will simultaneously, as we write a new app down here, we will write the old app up here, which we call swapping. But the swapping gives us some extra features. So the main point is that you put the old app into the new one. And then when you continue running the device, it will, as normal, hand over from the bootloader to the application and continue running the new app. Okay, let's go to the next slide. As I said, we want to swap. The reason we want to swap is that when you do DFU, you don't always know that the update will be successful. You are running new firmware on your device, and things can happen. You never know. So the thing I would suggest that you do is MCUboot has this feature called testing. When you upload a new application and before it is swapped, MCUboot will check a flag that is set on the image slot in secondary. That flag can be three things. It can be confirm, test, or revert. When you first upload it, it's recommended to use test. That means that it will swap here and then tag the old app that you had with revert. This means that on the next reboot, the old app will be swapped back into where it was. And the reason you do this is that gives you one boot cycle where it runs the new application, and in that boot cycle you can test it. If it crashes, then the device will automatically restart, as it usually does on faults, and it should do on faults. And since nothing new happened, it will swap back into the previous one. However, if you do your tests and everything is fine in the new app, then you can then it will tag itself as confirmed, and it will stay in space, and now that will be its the permanent image that runs. As you can see, this gives you some robustness so that you are able to test that your app runs before you know that it runs forever. Default MCUboot operations make it so that once you have confirmed this one that you're done with test mode and the old app is here in the secondary slot, the old app is here in secondary slot, you will not be able to change back again later. So you have like the one run for testing, or as many runs as you think you have, as long as it is in test mode, but once you've confirmed the image, then it runs. The reason for this is that you want to avoid downgrade attacks, as they are called, and this is that someone who wants access to your device and knows that it had a previous version of the application which has a vulnerability they could use, could, if it was possible, trigger the revert mode, or the DFU mode again, and then try to revert the old app into the new app. But we don't want to allow that, which is why you can only test the first time, or swap it back the first time, but once you confirmed, you're locked into it. Okay, that's how serial recovery and dual slots work for MCUboot, and this concept is the same between all DFU done on our devices that run MCUboot. So if you use LTE or if you use Bluetooth, the part that varies is just the transmission method. And once you got it into the secondary slot of the device, then the swap of MCUboot will be the same either way. Next up, I will go through some of the tools and systems in the nRF Connect SDK that you will need to know about when you are configuring MCUboot. These I've seen a lot of cases where people struggle with these concepts on DevZone. So I think it's a good idea to go through them and explain their concepts, because that will help you more easily work with them later. And I will also tell you how to use them, and in the hands-on later I will also show you how to work with those. And the Dev Academy work with them as well. There are two things. There's the Partition Manager and there is the multi-image build system. We start with the Partition Manager. The Partition Manager, as I said, the flash will be parted into different partitions. And this is something that's handled by software. And we use the Partition Manager for this. And when I say we use the Partition Manager for this, I mean that it is specific to the nRF Connect SDK, and it is not used in Zephyr. So beware of that if you use just vanilla Zephyr, as I like to call Zephyr without the nRF Connect SDK. The partitions are handled in the device tree. Nordic has made this to help us when we have a lot of different things needing partitions. We want to dynamically allocate space for those so that the user doesn't have to calculate all of the sizes themselves. And therefore we made a tool which we named the Partition Manager to manage your partitions. It's a script that runs in build time and sets up the partitioning for you. and it also has, you can get some of the data from it in runtime as well if you need to work with the data. Now, I want to mention that there is a requirement for MCUboot related to the Partition Manager, and this is that you need MCUboot knows about where the application starts and where the secondary slot is, so that it can swap. But since we cannot update MCUboot, we this information about where it starts needs to be set in stone. You can't change it. And the application here, meanwhile, is running and it needs to know where it writes this secondary image to. The application, however, can be updated, meaning that the information about where the secondary slot is and, for that matter, where the application lives, can be changed in the application. However, since this cannot change in MCUboot, we have a requirement that this cannot change for the application either. That's a requirement from MCUboot. For that, it is possible to set a static partitioning file for the partition manager, saying that this is the partitioning, and it's like this. Don't change this dynamically. I recommend that while developing, you use dynamic partitioning, and then when you're close to end of development, you freeze the partitioning and you keep it froze for all future development, so that you, when you make new DFU images, the partitioning will be the same for all future versions of your application. Now, if you ask, but what if I ever want to later add some extra storage, or like I figure I need less space for the application and more space for storage later? How can I fix that? The short answer is you can't. So you should plan for this and have some extra space, like some extra, have a partition outside the MCUboot partitions that you can allocate for to use later if you need it. And the second answer is that it is possible to run two bootloaders, in which case you can update MCUboot, where you and therefore you can change partitioning with that. I won't cover that here, nor in the Dev Academy course, but we do have documentation on running dual bootloaders. And you'll find this bootloader documentation that I am referring to, you will find in the Dev Academy course. It's mentioned a lot there. The page you see here is from VS Code, from our extension. And in your project, if you click the memory report button and then choose the partitioning tab, you can see an overview over how partitioning is set in your project specifically. This is a useful tool to get an overview over how your project looks when you're working with this. I can mention that pad is a space where MCUboot puts some metadata for the images that it will upload. And then over to multi-image builds. We have two images that we run. We have MCUboot and we have the application. And for example, for the nRF 53, we also have a network core image. When you develop your projects, you don't want to have to build a lot of different images in a lot of different places when you build a project. Preferably, developers would want it simple, we think, and then just build once, and then it will build everything that goes on your microprocessor, and then you can flash, and it will flash everything that goes on your microprocessor. We have an nRF Connect specific again system called multi-image builds that helps you do this. This builds first. You define. This works in the following way. You have an application that you build, and you define some images that goes in addition to that application. For example, MCUboot or a network core image. You can have multiple at the same time. And then When the application builds, it will also build the other images and define flash spaces, and it will define partitioning for those as well. And yeah, make sure that these fit together. It will configure all of them from the application, from your project, and then it will merge them into one hex file called merged.hex that you can flip to your, that you can flash to your device. Now, I forgot to mention on the Partition Manager slide, so I should just mention it now, that when you enable multi-image builds, Partition Manager is enabled. And yeah, that's when is Partition Manager enabled. Yeah, let's jump back to the slide. Partition Manager is not enabled by default for all nRF Connect SDK project. It is only enabled if it is needed. It is needed for multiple images, is generally will generally enable it for you. And but you can also enable it manually if you want to. But sometimes it will be enabled in your project when you don't know, like if you never heard about the Partition Manager and you just enable MCUboot in your project, then this will be enabled and your project will behave a bit differently, which is known to confuse people every now and again. So be aware of that and see the Dev Academy article if you want to know more about this, exactly when it is Partition Manager is enabled. I think I list all of the alternatives there. Okay, back to multi-image builds. I'm sorry if this was a bit untidy, but yeah, it gives you, it builds the images for you. I have an image on the next slide where I try to visualize this, how it will build things and order these things. Why do we need to know about multi-image builds? Well, we use this, we will configure child images such as MCUboot in your project. Meaning that to configure MCUboot, you need to know about this, so you know how to properly add MCUboot configurations. Yeah, I mentioned that it is in the same way as Partition Manager and nRF Connect SDK specific, so you cannot use this in vanilla Zephyr. However, we are working with Zephyr to add another similar system called sysbuild, which is also used for building multiple images. And we are slowly phasing out multi-image builds to use sysbuild. When sysbuild is ready, and that will be what we recommend, I will update the Dev Academy guide to cover sysbuild as well. So if you watch this Dev Academy a bit later on, make sure to check the Dev Academy course and see if I have added a section on sysbuild, and then that section will be relevant instead of this one, because things are done differently in that. Yeah, and just for your convenience, I added a link to multi-image build docs on this slide if you need that later. And all of these links will also be, like the Dev Academy course will have a lot more links for you to the images. And this image, there's a lot of things happening here. So I don't, it's not for you to understand completely. It's to give you some visual image on how this works. But at the end, the how you configure MCUboot is something that you can just learn without necessarily needing to know the system. Although this system will help you understand what is happening if you like that. Okay, the next image I have will show you how multi-image builds works, but this one is first an illustration of how it would work if you don't have a system to do it. Then the red image up here would be your application, for example, and the green one would be a bootloader. So then you would have to build each of them for yourself, and each would have their own configuration and code. And then you compile them each at their own, and you make sure to program them. And then you need to make sure manually that they have the correct addresses and go into the correct places in the device, like this. It is very possible to do this, but as you see, they are separated, they're not connected in any way, and you need to make sure that it's done correctly, and you need to do it twice. Now, this will then be how multi-image builds work. Then you have one main image, that would be, for example, the application, and you have several child images. The application has source code and configurations and so on, and the child image has the same. However, in addition to this, there is some partition information handled by the Partition Manager, which goes into both so that we know, since they get it from a common source. Usually configured, the Partition Manager information is usually configured in the main image as well, I should mention. But since they both get this from the same source, we know that they will have the same partitioning information and that nothing will go wrong there. In addition, the application has the ability to set some overlay configuration for the child image. And as you can see, it will go into here and add on to these bootloader child image configurations. And then together, the build system of the multi-image build will then automatically merge the image for you, so that you get a merge.txt that can be used to program the image so that you get these correctly, so that you know it's correct and you don't need to make sure of this. You just get the file and you know that merge hex file is what you want to program to your device. Yeah. If you want to look more at this, it's explained a bit more into depth, I hope, in the Dev Academy course as well. Yeah. There is I will show you in the hands-on part, but let's jump back. The multi-image build docs will show you, has a page, well, it's a documentation page, and it tells you how to add configuration to MCUboot. You need to put it in your project in a specific way with specific names. And I will show you how to do that in the hands-on, but you can also learn that on Dev Academy course. I have some exercises where you will learn that there. And now, after we've gone through that, we will go to the demo. Here I have the nRF Connect SDK installed via the nRF Connect for VS Code extension that we have. And you can learn this by following the Dev Academy Fundamentals Guide. I use Ubuntu, but the steps here should work for any operating system. Now, the first thing I will do is that I have a DK, 52840 DK, connected to the PC. Let's make sure that it is connected. You should see it down here. Yep. I will create a new application based on the Hello World sample. Yes. Yeah, and open that. Now, I trust myself. Now that we have that, we will use default configurations for the 52840 DK, and we will build it. And while it is building, I can say the plan for this demo. I will show you two things. I will show you how to do a serial recovery with single slot over UART, and then I will show you how to use Bluetooth low energy, and then I will get my phone and share the phone screen on the here to do FOTA with dual slots on the DK. So this boat uses a 52840 DK, but you can use other development kits as well if you want. For the Bluetooth part, you need a kit that supports Bluetooth. But for the serial part, you should be able to use any of our development kits. Now I will flash this, and then I will open a terminal so we can have a look at the nRF serial terminal connected to the development kit. And then I will connect, find the device, and I will connect it to the terminal. And if I reset the device like this, we should see the logs. Here we go, hello world. So first thing we want to do is to enable MCUboot. That we do in project.conf. And here we do config bootloader and then MCUboot equals yes. And we just simply flash that and we clear this terminal so we see a new log. And then with the nRF Connect SDK, there are a lot of configuration options. So some of you might think, how should I know about this? That you say exactly config bootloader MCUboot. There are 3 ways you can learn about this. It's either through the Dev Academy course. When you follow that, you'll learn that this exists. If you look at our bootloader documentation, you will find this. Or you can go through our samples. Some of them use this enable MCUboot and therefore use this configuration. Now with MCUboot enabled, we see that we have this new log on top, which shows that MCUboot is running. Yeah. The first thing we will do is to configure the MCUboot child image and disable logging. Just to show you, because this is nice for debugging, but once you go to production with your device, you want to remove logging so that you don't, and remove serial so that you don't use more power than you need to. And I will show you how to do that for the child image. And just to show you how to configure those. For that, we will open a new tab to our technical documentation. We will go down to the nRF Connect SDK here, and this is the new documentation page. And I will follow that now because it's coming up. I think it is still in beta, but we'll use this so that this webinar will be relevant for the future as well. And yeah, this has the same setup as the same pages as the old documentation, of course. So to learn about child images and how to configure MCUboot, I will go to configuration and building here. I will go to bootloaders. Then, and this will be the base page that you use to learn about bootloaders. Then we will go to customizing the bootloaders because that's what we want to do. And we will scroll down to using custom project configurations right here. You of course would read this, but I have read it before, so I know that this is the part we want to do. I prefer to use child images and this folder, or the child image folder, to configure my projects. I think that is quite tidy. So I will learn how to do that. I will click the link, linking me here to show how to do this. Now, this tells me that I can use a child image folder in the application and then put files with specific names in there to configure the child image. This comment right here of code, it is a bit untidy as is, so I like to create a new file in Visual Studio Code and paste it in here so we can easier see it. Zoom in once, I think. Take away this for now. Here we can see that this is the child image as sample specifically, because child images runs from some sample somewhere in the nRF Connect SDK, which is basically a project. For MCUboot, just to show you where it is, you go to NCS and then to bootloaders, MCUboot, and then under boot and then under Zephyr, and this will be the code, like the application that runs MCUboot. And you see some parts that you recognize, like project.conf, cmake list, and a main.c somewhere here as well. There it is. I don't recommend that you change any of these files because that will make changes to the nRF Connect SDK, and you generally want all of your changes to be to your projects. And that's where the overlays comes in, because in my directory for the project I have, that is Hello World, I got like the files project.conf that you expect, and then I can create a child image directory with that specific name. Now with that, I can create a file, and here we always exchange the ACI name with the name of our child image, which in this case will be MCUboot. And then if I create a file called MCUboot.conf, that will be used together with MCUboot configuration. I can do the same with device tree overlays. An alternative to this could be to create an MCUboot directory in here named MCUboot, and then create a project.conf inside there. But keep in mind that will be used instead of MCUboot configuration, so it will overwrite it. Because of this, we will use MCUboot.conf. Now let's do that. We go to our folder, we will create a new folder named child image, and then we will create a file here named mcuboot.conf, and in that we will disable serial. That will disable serial for our project. I can close this one, but yeah, so just keep in mind that this yellow text here, this code, these comments are very useful for learning how to configure this child image folder and what files need to be named. Okay, with this, we should be able to flash the project again, and I can see if I can get back the logging, and I will clear this. I created a new file, so I should do a pristine build here. Let's see, do a pristine build for it to find a new file. And there with the pristine build, you see that it does not log for MCUboot anymore. Now, furthermore, yeah, now we've done that. The next step would be to enable serial recovery. So we remove this for now. To enable serial recovery, we need to find configurations option for MCUboot. If we have a look at our kconfig search, which isn't here, well, config search nRF, then we go to the old documentation. If we search here and we search for boot and serial, we cannot find any options for that. Or serial boot, there's nothing here. And that is because MCUboot is a sample, as I told you, and this search only returns global configurations. I think the easiest way to find configurations options for MCUboot is to use this kconfig GUI. But if we just click this, we will get the configuration for our application, and we want this for the child image. So the trick is to open the build folder over here and then click on MCUboot. Now if we use this, you see that the kconfig menu is for MCUboot specifically. So here I can search for serial recovery like this. We can make the logs a bit smaller. And here we see we have an option for serial recovery. Then I can jump to definition. I like to do it this way. And I can copy that and I can paste that, and I need to put config in front of it, and I enable it inside mcuboot.conf. Now, next up, I like to as well search for MCUboot LED. And here I will find turns on LED when the device is using MCUboot. So I will enable this configuration as well. And this is just for convenience so that we can see it. It will help us later. If I now build this, we will get a build error. Because I've done this before. And it says that the Zephyr UART console must be disabled if the serial adapter module is used. And then I'm thinking, which config is this? So I click on the file where the error comes from. And then I see that this depends on, this warning comes if this is not set. So I'm assuming that this will be the configuration they are talking about. So I will disable this, and then I will build and flash again. Now we should see from our terminal that it will print hello world again. And this is normal, because the serial recovery will do nothing if you don't hold the button. The way serial recovery works is that you need to hold one of the buttons for MCUboot to enter cellular recovery mode. You could also configure this to wait some seconds and wait for a command as well. But by default, it will wait for a pin triggered. So if I now reset the device while I'm holding button 1, I should look at my DK and see that LED 1 is on, and indeed it is. I can now talk to MCUboot, but for that I need a tool on my device. So we need to install this tool. If we go to our bootloader, back to our bootloader configure documentation, we can go to Device Firmware Updates. As well, that is under Configuration and Building, Device Firmware Updates. Here, Device Firmware Updates, yeah. Here we can see that we have a list for different tools for sending updates and for receiving updates. Right now, I need a tool for sending the update on my computer. You could choose between these, and it depends on what device you want to send it from. But for now, I'm going to use the command line tool. This is called MCU Manager Client. And just a heads up, there will in the future be other versions of this that we can that are available. So keep an eye out for the new documentation in the next version of the nRF Connect SDK, because then we get the Zephyr documentation in, where it lists some other tools. But for now, I will use this tool. Now with this tool, to install this, I will have to install Go, and I have already installed Go on this computer. And to install this, the documentation here is slightly off, so I will have to look for MCU Manager and Zephyr like this. It's beta documentation after all, so we expect that. And if we see the new version of Go, which I have, this is the command to use. So I will paste that into here, and it will install this application. In addition to that, I want, when I first did this, I learned that MCU Manager is not in path yet, so I can't run that. So I need to export path, and I found this just by searching Stack Overflow for this, for how to add the Go packages to my so that I can run those. So if I do this, we should be able to run MCU Manager. Here we go. Thus we can see that when we run it and it returns all of this help, we know that it is installed correctly and that it is in path. You should be able to install this to Windows as well, but for Windows I don't think you need this path thing. You might need another way to do that. Windows. Now with MCU Manager, we can take and we can copy this command right here. It's to make it a bit easier to run. It says copy, does it? Well, let's just click the copy, and I can do clear to clear this, and I can paste that. So this will add a connection type called ACM0. You can name it whatever you want, but that is for terminal, the device ACM0. For Windows, this command is slightly different, so I advise you to check the Dev Academy course where I give the command both for Linux and Windows. It added this profile, so then I can do MCU Manager, .c, where I name the com, which is ACM0, and image list, and since the development kit is in serial recovery mode, which I can see because LED 1 is lighting up, it returns over the USB, it returns less. If it does not do this, there are two typical issues. One of them is that you have logging enabled somewhere, so it's a good idea to close that. The other one is that the virtual disk that our debugger chip on the D case have enabled might be enabled because that takes up a lot of the space on the USB lines. So to disable that, we can do JLink XE, and then we can do MSD disable like that, and then exit, and then we need to repower our development kits after that to make that effect go into, make that change go into effect. Anyhow, okay, now let's re-enter bootloader mode by resetting the device. Press reset and hold the button. And now we are ready to do DFU. To do DFU, we need to change something in the application so that we can see the change, and also it won't do DFU for the same file because that for the same image, because that is a waste of resources. So we go in here and we change this to hello world again. Now with this we build, and here it's important that we only build and don't flash. And with that we follow here. We had the image list option here. That's where I got that from, if you were wondering when I got that. And then there is the image upload, and this one says that we should use Zephyr.sign.bin, but instead in the nRF Connect SDK, we want to, under configuration and building, I think there is a output build files, and you also find this page under bootloader configuration documentation. You found MCUboot output files, and we could use either DFU application.zip or app-update.bin. Can be uploaded to a server as a FOTA image, to upload here. So then we can copy, let's say, I remember it, but this was also on the MCU Manager documentation, MCU Manager -C ACM0 image upload, and then we do build, and then the app update is inside the Zephyr folder, app-update.bin, and the path to this file is something you just have to find or learn, or you can search for the file as well, but that's where it is. So with that, you see we are uploading it slowly but surely. And now that it has been uploaded, we can reconnect to the terminal for this here. And then we can reset the development kit, and we see that it prints again. So we have successfully done serial recovery. Now, next up, we will do the second part of the demo, which is to do FOTA, update the device over Bluetooth Low Energy. To do this, I first want to flash or do the Bluetooth sample. So let's create a new application from a sample and then do the LED buttons, Bluetooth peripheral LBS. So we'll create a new application for that, and we will open that. Here, cross out these. Now we will connect to the logs for our development kit again, so we can see the logs, and then we will add a build configuration, which will be just a default configurations for the 52840 DK, which we are using. While that builds, I will go to our documentation, and I will go back to our top page of the documentation. To learn how to enable FOTA, we will go to device configuration, and then we will have a look at the nRF 52 series, and then the the developing guide. Under here, we see that we have some chapters for FOTA updates, and we want to do FOTA over Bluetooth Low Energy. We're going to have a look at this soon, but first we will see that we are able to flash the FOTA sample, no, not the FOTA, the peripheral LBS sample, which we will add FOTA to the device. And as we can see, logs are looking good. And we can go to this is my phone over here. And if I scan here, you can see that we have the Nordic LBS that we can connect to. I'm using the nRF Connect for Android application, which is also available for iOS. But you could also use, for the same DFU purpose, you could also use the Device Manager application. It's what you like best. Yeah, we can see that we have this one, and we can read the button state like this. Button is released. Yeah, and we can set the LED if we want to. Yeah, it works as expected. So we disconnect that, and we cross it out, and then we see it here again. So, and yeah, we see that that was our device as well in the logs. Now we want to add DFU. So we're going to go to the config files, and we will, from this, we enable this option here. Yeah, and we of course need to enable MCUboot as well. So we enable MCUboot, and we enable OTA. I should mention that this configuration option is named NCS sample. So it is an option that we add so that we easier can add over the air for our samples. If you add this, you also need to enable Bluetooth and start advertising, because this won't do that. So you can't just add it to the Hello World sample. That is why we add it to a Bluetooth sample. If you are going to use this for your device, I recommend that, maybe you start by testing this, but once you know that this works, you go into this and you see all of the things that this option imply and select, and you figure out which of those that you need, and you set those manually in your application. It will require some more settings in your project.conf, but it will give you a better overview over what you really need. For example, this one assumes that if you have external flash, you need QSPI. So if you have an external flash that runs on SPI, this sample option will not work for you. But our DKs for the 52840 and 53 use QSPI for external flash. So yeah, as you can see, this assumes some things that might not be true for your project. Anyhow, now that we've done that, we will build the project with the new configuration. And for this, it will use the default MCUboot configuration, because by default, MCUboot uses dual slots. And it will just check the secondary slot if there is something there when you start it. And then we will flash that to the device. And I can clear the log in the meantime, so we can see that there's a new log and that everything is as it should be. Here we can see we are advertising as expected. Now we can connect with the phone, and you can see what is new. There is this DFU symbol up in the corner. If you use the Device Manager application, nRF Device Manager, there is a chance you won't find the device until you have enabled DFU, because that will scan specifically for DFU. Now, the next step you need to do, which I've already done because it takes a bit of time, is that you need to transfer the app update file, which we used in the previous one from your build folder, to the phone. and I prepared that file before I started this, so that so that you wouldn't have to wait for me transferring that. So we start DFU and we choose this file, and here we have some options. We have test and confirm, we have test only, we have confirm only. These options are better explained in the Dev Academy course. I think I mentioned them earlier as well, but test means that you just mark it to run once and don't revert it. But if you want to know about this Dev Academy course, then if you want to know more about this, check the Dev Academy course. So we do test and confirm now, and then you see it connects and it starts to DFU the file, and you can follow it. And then when it is done, it will restart the device and run the new application, which will then be on Bluetooth. And then we'll connect again, and when you know it can connect again, it will assume that the new application is fine and then do confirm. In your application, you might want to do a bit more verifying before you confirm the application, but that is up to you, up to how much testing you want to do. As we can see here, yeah, it restarted again, and now it is, if we have a look at the logs from that is good, we see that we started, we connected, and then it entered test mode. So it started swapping the images. It started swapping MCUboot primary and MCUboot secondary slots. And here we are running the test sample. You can see that it prints this new thing that I added. Check out Dev Academy is the test thing that I printed, which was not there before. And then, yeah. So now if we reset the device again, we will see that it is indeed not in test mode anymore. And because it was confirmed, it will still print this out and it will do that forever. Yes. There are a lot of, and that is how fast it could be to add DFU to the device. It is, if you want to add some options, such as add external flash to it, there are some extra steps you will want to do. I don't have time to go into that now in this webinar. However, you will be able to find this in the Dev Academy course, and there is also explanations of a lot of these things under our documentation, both under device guides and also under the bootloader documentation that I showed you earlier. I hope you have enjoyed this webinar, and I think there's time for some Q&A.
Thank you, Sigurd, for this great presentation and awesome demos. And as Sigurd mentioned, this webinar is just a small part of a complete lesson that covers a lot of use cases, not only doing serial recovery or FOTA over Bluetooth Low Energy. No, it covers actually a lot of cases. So it also covers how you can do FOTA over Wi-Fi, how you can do FOTA over cellular, and you can also, there are some corner cases for the 5340 since it's a dual core device. There is also DFU over USB, DFU over external memory. All of this is dedicated, there's a dedicated lesson for this. It's done by Sigurd, and it's in the nRF Connect SDK Intermediate. That lesson is lesson 8. So the nRF Connect SDK Intermediate, it's not available now. It will be available tomorrow. So please make sure to go to Dev Academy and register to always get notification on these new courses. And also something to mention, like the content on Dev Academy is always up to date. So that's where you go to kind of like learn about things like DFU and FOTA. And for that, I think we're ready to take some Questions?